Welcome to the explainer. Vectorless RAG, when LLM reasoning replaces vector search. We are jumping right into a massive, rapid shift happening literally right now in enterprise AI architecture. For a long time, vector databases have been the absolute default backbone for Retrieval-Augmented Generation, or RAG. But, what if the default isn't always the best choice? Today, we're breaking down this new approach where large language models actually bypass traditional vector similarity search entirely. Instead, they use direct reasoning to find exactly what you need.
Okay, let's dive into this. Take a look at this real-world financial query. Imagine an analyst asking this exact question. It spans multiple documents, it requires cross-referencing, and it relies heavily on strict regulatory definitions. When you feed a complex, multi-hop question like this into standard RAG, it instantly breaks. But why?
So why does it just fall apart? Well, it breaks because standard RAG relies on chunking. Basically, traditional systems fragment your documents into disconnected chunks and convert them into vectors. They assume that the semantic meaning of your query will geometrically align with the answer. And for basic facts, sure, that works. But for our financial analyst, chunking literally destroys the structural context necessary to link that Q3 performance with a specific 2024 credit risk amendment. A similarity search just grabs chunks that sound vaguely like the query, completely missing the actual logical connection. And this brilliantly illustrates the massive paradigm shift we're talking about today. We're moving from a basic search problem to a dynamic reasoning problem. In traditional RAG, you embed a query and retrieve the top chunks. But in vectorless RAG, the LLM actively reasons over document summaries, and then it triggers a full-page targeted retrieval. There's absolutely no vector index needed at all. It naturally handles multi-document reasoning because it actually preserves the structure of the original document. So how does it actually work? We're looking at a four-step engine: indexing, reasoning, retrieval, and generation. It's called the page index architecture. Let's walk through exactly how each stage operates technically, but we'll keep it really simple, starting with the foundation. Step 1 is structured document indexing. Instead of embedding those shredded chunks, we use an LLM to generate a human-readable structured summary for every single page or section of a document. It pulls out the primary topics and key entities, like specific dates or financial codes, and cross-references. We store these summaries in a lightweight JSON file, which is basically just a simple text record or a standard relational database. No vectors, no complex embedding models, just a perfectly clear, auditable index of what is on every single page. That brings us to step 2, reasoning-based retrieval. When our financial analyst submits their query, the system shows that summary index to the LLM and asks it to literally reason about which pages are needed. The LLM's internal process might output a trace saying, okay, I need page 4 because it defines the PEP alert escalation tiers, and I explicitly need page 17 because it contains the 2024 credit risk updates. It tells you exactly what it needs and why it needs it. Now, what's really interesting about this slide is how stage 3 completely changes the game. Once the LLM selects page 4 and page 17, the system performs full page retrieval. It fetches the complete, structurally intact text directly from the document store. That means those vital financial tables, numbered lists, and exact phrasing are perfectly preserved. We aren't reconstructing fragmented pieces, we're providing the exact structural blueprint that traditional chunking would normally destroy. Finally, we reach stage 4, grounded generation. The LLM has handed the user's query right alongside these complete, structurally intact pages. Because the model has this much richer, higher quality input with known provenance, it just doesn't have to guess. This drastically reduces the risk of hallucination simply because we aren't forcing the model to fill in structural gaps with its own parametric knowledge. And this built-in auditability is exactly why highly regulated industries, especially in finance, healthcare, and law, are adopting this so quickly. It enables that complex, multi-hop reasoning we talked about. It preserves those crucial financial tables. But most importantly, that reasoning trace from stage 2 acts as a native built-in audit trail. You know exactly why specific documents were selected. For strict legal compliance, having a system that can explicitly explain its own retrieval decisions is an absolute necessity. But, we need to be completely objective here. Vectorless RAG is not some magic bullet for everything. Take a look at these trade-offs. Because you're using an LLM to actually reason over summaries, latency drops from milliseconds down to seconds. The cost per query is significantly higher because of those extra LLM calls. And if you're dealing with a massive scale, say hundreds of thousands of pages, feeding all those summaries into a context window just isn't feasible yet. Traditional RAG definitely still wins on raw speed, cost, and massive scale. Let's move to and see how this builds perfectly into the future of AI, agentic systems. Traditional RAG is kind of like a one-way street. Query goes in, chunks come out. But Vectorless RAG actively empowers agents to iterate. The agent plans its retrieval, retrieves the pages, reflects on the answer, and then, if it notices a gap in its knowledge, it simply replans and retrieves again. You can ask a vector index, hey, what did I miss? But an LLM reasoning over summaries can do exactly that. So the crucial point is this. Here's the explainer recap. Vectorless RAG replaces vector cosine similarity with direct LLM reasoning. By retrieving full intact pages, you preserve the precise structure of things like financial tables and legal clauses, and while you for sure trade off some latency and cost, the built-in auditability and precision make it an incredibly powerful tool, especially as we move toward long-context agentic architectures.
Which leaves us with a fascinating question to consider. The shift we're seeing here reflects a much broader pattern in AI. As our models become more and more capable at reasoning, is it time to stop hard-coding retrieval logic into our infrastructure and instead move it directly into the model itself? Think about what that actually means for the intelligent systems you use every single day. Thanks for joining this explainer, and we'll catch you next time.